This is from Tamil Nadu State Board book, Physics book +1, gaseous state. This is a very, very important topic. Let us have a fast run through. The major contents of this gaseous state is, please take down, laws governing the ideal gas. This is very important. So point number 1, this is a very important topic. What are the laws associated with the ideal gas? So first of all, we should know what ideal gas is. Secondly, we have to demonstrate these gas laws in various real life situations. So gas laws in a real life situation, this is second concept. Third, we need to derive an ideal gas equation so that we can perform calculations and problems based on this. So this is the third aspect of this lesson. And we need to talk about the deviations from ideal behavior. So we cannot say that is all gases are ideal. No gas is ideal, actually speaking. All gases are real, but how they deviate from the ideal behavior. So we need to discuss that aspect. So that is fourth concept. And just like we have got ideal gas equation, which is meant for ideal gases. Similarly, for real gases, we need some gas equation, and that is called van der Waals equation. So we should know the derivation of van der Waals equation. So this is point number 5. And we should know something about the Graham's law of diffusion. Okay, diffusion means what? The spreading tendency, is it not so? Sixth point is Graham's law associated with the diffusion of gases. Then when it is diffused, the opposite term is compression, is it not so? We have to discuss about the compressibility factor. So that is the seventh concept. And then we'll be explaining about the critical phenomena like critical pressure, critical volume, critical temperature, etc. Okay, so this is point number 8. And then we have to derive the critical constant in terms of van der Waals constant. That is, we have to arrive at the relationship between the critical constant and van der Waals constants. Okay, so this is concept 9. Then explain Andrews isotherm of carbon dioxide. Iso means the same, therm means temperature. So at constant temperature, what about this pressure and volume, the variables, how they behave? So we are going to study about this in a graphical way. So that is the 10th concept, that is Andrews isotherm for carbon dioxide. Then we'll be explaining about the Joule-Thomson effect and the coefficient of liquefaction of gases, that is 11. So we'll be discussing all these 11 important topics under gaseous state. See, first of all, when you go through the lesson, you should be able to identify the topics involved, the subtopics involved, and make it as a topic tree. And you should be able to, that is, tell the contents of this lesson. Okay, the key points. What are those key points? That is ideal gas law 1, that is laws of ideal gases. Point number 2, that is gas law demonstration for a real life situation. Point number 3, ideal gas equation derivation. Then this can be asked as questions also. And concept number 4, that is deviation from ideal behavior. Question number 5, derive van der Waals gas equation. Question number 6, Graham's law of diffusion. So state Graham's law of diffusion and explain. 7, what is compressibility factor? Explain. 8, critical phenomena. 9, the relationship between critical constant and van der Waals constant. 10, explain Andrews isotherm for carbon dioxide. And the 11th is, that is what is liquefaction. In fact, this liquefaction is based on the Joule-Thomson effect. So we will be explaining about all these 11 topics very neatly. Okay, right. Now, so here the gas laws, it starts with the gas law. First of all, when you talk about gas, you should know the parameters involved. Pressure is a very important term, please note down this. So what is pressure? Force acting on unit surface area. Force is given in terms of Newton. So area means meter square. So you can put it as Newton per meter square. Otherwise you can make use of kg ms power minus 2 also, because the force is nothing but what? That is MA. M stands for here kg. It is represented as kg. A, that is the ms power minus 2, that is acceleration. So in both ways we can explain, and you should be able to tell the various units of pressure also. For example, for pressure, it can be represented by that is Pascal. The unit is Pascal, okay, and that is represented as, that is PA. Simply speaking, PA, okay. And then next we have atmosphere, that is represented as ATM. And first of all, 1 Pascal is nothing but 1 Newton per meter square. And atmosphere, this is the regular unit that is used. So 1 atmosphere is equal to, that is 1.01325 into 10 power 5 Pascal. Okay, so you can bring this in a scientific term or scientific notation also. And then millimeter of mercury. So in this case, it is represented as a pressure column, millimeter mercury column. So 1 mmHg is equal to 133.33322 Pascal. In fact, the room, that is atmospheric pressure, is represented as 760 mmHg. And similarly, 1 atmosphere is the atmospheric pressure. And bar, 1 bar is 10 power 5 Pascal. 1 torr is equal to 133.322 Pascal. Similarly, PSI, in fact, this kind of units, pounds per square inch, it is called British thermal unit. So this is the one we use for that is measuring inflation of the pressure, tire inflations. Okay, so to measure the tire, okay, the inflated air in the tire, we use this PSI. So we put, that is 25 PSI, 32 PSI. For front wheel put 25, for back wheel 32, something like that. So we have to consider this one also. This is the more practical industrial units. Okay, right. Then Boyles Law. So we were discussing about the various laws associated with the ideal gas. We have Boyles Law, Charles Law, Avogadro's Law, Gaseous Law. So these are all the very important laws associated with, Boyles Law, Charles Law. So Charles Law 1 and 2. So Boyles Law, Charles Law, Gaseous Law, Avogadro's Law. All these laws are governing the ideal gas. But you should remember, no gas is ideal. You may ask, so for no gas is ideal, why should we need a law for ideal gas? Because we need to put some standards. Even though we are unable to maintain the standard 100%, but there should be some standard. For example, 0 centimeter, can you show me? So we need some standard from which we had to measure. Okay, right. So Boyles Law, it states that is the volume of given mass of a gas is inversely proportional to pressure. Don't go by the statement. In my opinion, always go by the equation given, and based on that you can define also, you can state the law. For example, take this. What is this? V. V stands for volume. P stands for pressure. So the volume is inversely proportional to pressure. So this is the simplest way of telling Boyles Law, right? But let us modify slightly. Volume of a gas. When I say volume of what? Gas. So the volume of a gas is inversely proportional to pressure. And third step, for any amount of gas, no. The volume of given amount of, that is very important. Given amount of means it's a restricted amount. So the volume of given amount of gas, the volume of a given mass of a gas, this amount represents mass. So the volume of a given mass of a gas, you just follow me how I refine the language. So the volume of a given mass of a gas, got it, is inversely proportional to pressure. When the pressure increases, volume decreases. When the volume pressure increases, decreases, volume increases. Inverse proportionality. So the volume is inversely proportional to pressure at which stage? At constant temperature. Okay. So this is the way you can maintain, and therefore you can simply put that is V is inversely proportional to P at constant T. That's all. This is the way you can simply represent the Boyles law. Now what you can do, P, for example, when you want to remove the proportionality, you have to introduce the constant. Okay, when you want to remove the proportionality or replace the proportionality by equality, then you have to introduce a constant K. Therefore, V is equal to K into 1 by P, where K is the proportionality constant. Now you can bring this PV here, so PV is equal to constant. So when there are two situations, then you can say P1 V1 is equal to P2 V2, that is equal to constant. This is the best way of representing Boyles law. So when you are asked what is Boyles law, very simple. P1 V1 is equal to P2 V2, that is equal to P3 V3, that is equal to P4 V4, that is equal to constant. It means the product of pressure and volume is equal to constant at constant temperature. In other words, you can make use of this equation. So the volume of a given mass of a gas is inversely proportional to pressure at constant temperature. Like this you can mention. Now probably that is, they would have shown some U-tubes like this, where this is called the manometer. Mono means a single, manometer. With the help of the single column you can measure the gas pressure. Okay, so this is the volume, and this is another volume, and this is another volume. So this is full volume, this is half the volume, this is 1/3 of the volume. Okay, with respect to that, now you can find, because of the pressure, atmospheric pressure, it may change. So thereby it changes the length of the column which is filled with the mercury, and that is why the pressure is also expressed in terms of mmHg. How much height is observed because of the pressure. In fact, atmospheric pressure is 760 mmHg. Okay, right. Next, and that's where they are put. So are you able to understand this? Okay, so that is the room pressure, atmospheric pressure, right? Okay. Now let us consider this graph where we have the 1 by V of volume, because we already told it decreases with volume. So we can take the reciprocal of the volume. So 1 by V is on the x-axis, that is given in cubic decimeter, per cubic decimeter, because the volume 1 by volume. So 1 by decimeter cube means a decimeter power minus 3. Okay, decimeter power minus 3 means per liter. Okay, so 1 decimeter cube is equal to 1 liter, right? And then here pressure is given in atmosphere. So when we plot this graph, we are able to get a linear graph like this. So let us consider, that is atmospheric pressure, I mean the pressure in terms of atmosphere on the x-axis, and y-axis the volume in cubic decimeter. Decimeter cube is equal to liter. Now with the increase of pressure, I am going on increasing the pressure, what will happen? The volume comes down. Let me consider this is the piston, a barrel. So inside which now the piston, it goes like this. Okay, right? It goes like this, piston. Okay, now when you compress the piston, when you pressurize the piston, what happens? The volume is getting reduced. Are you able to follow? Pressure is increasing, volume comes down. When you expand it, what happens? Volume increases, pressure comes down. Are you able to follow? So this is the important aspect he has found, and that is interpreted as graph here. Okay, right. Next. The consequences of Boyles law. I think that is, I hope now you can go through this so that you can very well understand. Then what are the consequences of Boyles law? Let us consider P1 V1 is equal to P2 V2. That is another way of representing the Boyles law. Now what you can do, we know mass by volume is equal to density, right? So instead of V, we can put M by D. Got it? So I can put P1 into M by D1, because mass is same. I am maintaining the same mass. but the density of two gases may be different. So in that case, P1 m divided by d1, P2 m divided by d2. Are you able to follow? So now m can be cancelled, and in that case P1 by d1 is equal to P2 by d2. So it means what? The same Boyles law can be interpreted in terms of pressure and density. Are you able to follow? Right. So from this it's obvious that is density of the gas is directly proportional to the pressure. Denser the gas, more will be the pressure. Okay, right. And you have got some natural phenomenon like this. You can go through these examples. And let us talk about this. For example, you have got the piston and barrel assembly. Now you have got some gases inside the barrel. Okay, cylinder. So the pressure is 1 atmosphere at room atmospheric pressure. Okay. Now let us pressurize it. Now it increases to 2 atmosphere. Are you able to follow?
Yes.
And what about this? Here 1 decimeter cube, the original volume. And the volume will also be changing, Okay, so we can find out. And what about the temperature? The temperature it is maintained as constant. So based on this P1 V1, P2 V2 formula, we can work out what could be the pressure, what could be the volume, etc. Okay, so that will be useful for calculations also, and that is why we have used this problem, used this equation for finding out the problem solution. Okay, right. Then Charles law. So Charles law relationship states that V is directly proportional to T. This is Charles law 1. So we have to introduce the constant. So V is equal to KT. So V by T is equal to constant. So in that case, V1 by T1 is equal to V2 by T2. Are you able to follow? This is Charles law. The same Charles law can also be represented in pressure also. So where P is directly proportional to temperature. So P is equal to KT. Are you able to follow? So P1 divided by T1 is equal to P2 divided by T2. So like P2 divided by T2. So this can be illustrated like this. So this is Charles law 1, Charles law 2. And when we consider, and they have given some examples, you please go through that. Then we have here volume, and that is equal to, that is MT plus C, where this Celsius and C or degree Celsius, the temperature in degree Celsius, okay, that is kept constant. Now V is equal to MT plus C, okay, and C is constant, M is also constant because mass is constant. Now when T is equal to 0, okay, and what happens, VZ is equal to C, and we can find the slope here. You can have this graph. Now in this graph they have illustrated how the volume changes with respect to temperature. For example, let us consider x-axis where you have got the temperature, and y-axis we have mentioned the volume. With the increase of temperature, the volume is getting expanded. With the decrease of temperature, the volume is shrunk. Okay, it is decreasing, right? And here these things are very important. For example, so that differences has been interpreted in terms of delta. So delta means initial final volume minus initial volume. Okay, so based on this they have arrived at, and you should know something about the Kelvin temperatures, etc. So you have got the Kelvin scale. Okay, so this table is very important, because 273 Kelvin, that is absolute scale of temperature. Okay, 273, that is 0 Kelvin, that is equal to minus 273.15 degrees Celsius. Never forget this. And you should know the freezing point, boiling point in terms of Celsius as well as Kelvin. And you should understand at what temperature, you know something about Fahrenheit and Celsius. In that case, that is a different thing. And at what temperature Fahrenheit and Celsius will be equal? You don't know. Minus 40. Okay, do you know? Minus 40. Minus 40 degrees Celsius is equal to minus 40 degree Fahrenheit. We can work out the solution, proof also for that. Then now we have got another example. So based on this Charles law, we can work out this. Then Gay-Lussac's law. Gay-Lussac's law states that there is a ratio between pressure and temperature that is always constant. So in that case, P by T is equal to constant, means P1 divided by T1 is equal to P2 divided by T2. And Avogadro's hypothesis, this is very important. Avogadro, he said, that is it contains equal number of molecules at standard temperature pressure, STP we used to say. Okay, now this is called Avogadro's volume. So Avogadro's volume and the number of molecules will be ratio in a proportion. So it means V1 by N1 is equal to V2 by N2, where V1, N1 are the volume and the number of moles of gas at that particular value. Okay, then ideal, and what is Avogadro's number? The number of moles per mole of a gas. Okay, so what is that? 6.02 into 10 power 23. Okay, like 1 dozen is equal to 12. Then we have ideal gas equation. Now we can combine all these law, that is the Boyles law, Charles law, Avogadro's law, where we can get PV is equal to nRT. This is called ideal gas equation, and you can follow this. Okay. Yes, and you should be able to arrive at the R constant, that is R is a proportional constant, it is called universal gas constant. So you got this, and R can be brought here, so that you are able to get R is equal to PV by NT. Okay, and based on that you can substitute accordingly and get various values of R based on the input. For example, one value of R is 0.821 decimeter cube atmosphere per mole per Kelvin when you are taken 1 atmosphere as pressure, and 22.414, that is Avogadro's volume. Okay, and what about this 1 mole? And this one is a T. So T represents what? Temperature. So this is 273.15 Kelvin. So likewise, by changing the units, we are able to get different values. So all must be noted down. So you have to remember all these things. Are you able to understand? Right?
So for different gases, it will vary.
Yeah. So it's correct. Now the Dalton's law of partial pressure. So when you got more than one gas, for example, atmosphere contain carbon, carbon dioxide, carbon monoxide, hydrogen, oxygen, nitrogen, all these. So let us call the individual partial pressure P1, P2, P3. Okay. So the sum of all these pressure is equal to total pressure. So this is called Dalton's law of partial pressure. Okay. So because every gas has got individual capacity to prove its own presence, so that is called partial pressure. In fact, this partial pressure, so here we can say for everything we have got the ideal gas equation. So in that case, P1 is equal to N1 plus RT by V, P2 is equal to N2 into RT by V. So likewise it goes. So P total is N1 plus N2 plus N3 of RT by V. Okay, so therefore P total is equal to N total into RT by V. This is a very important equation. Okay, right. Now, and the partial pressure, okay, this can also be, that is given in terms of chi. Chi means, it is called chi, that is called mole fraction. What is that? Mole fraction. So when you got a total pressure, when you multiply by a particular component, for example, chi 2 means, let me consider two gases. Okay, what is chi 2? Chi 2 is N, yes, exactly. So N2 by that particular fraction, no, N1 plus N2 into that total pressure. So this is called, similarly, chi 1. Okay, so chi is the mole fraction. What is the portion of that particular component divided by total number of moles? And in terms of that is a partial pressure, means you have to multiply by the total pressure. Okay, and right. So far I have discussed up to the Dalton's law of partial pressure. So we will continue in the next class about the other aspects also. Okay, and you should remember this table, very important one. Please take down and memorize and make it as a flashcard also. Right. and this is called van der Waals equation of state P plus A by V squared into V minus B. For n number of moles, P plus A n squared divided by V squared into V minus n by is equal to n naught T. So you should be able to derive the equation also. So the relationship between critical constant and van der Waals constant. Which are van der Waals constants? This A, B or van der Waals constant. Okay. So here it is given. The derivation is very, very important. Okay.